Hi, in this video, I will be showing you problem number 31 of chapter 11, section 6. Use any test to determine whether the series is absolutely convergent or conditionally convergent or divergent. Sigma, n varying from 2 through infinity, negative 1 to the exponent n, ln of 3n. So let's recap the ideas of what we mean by absolute convergence and conditional convergence. If sigma of absolute an is convergent, then sigma an is said to be absolutely convergent. If sigma an, the series is convergent but not absolutely convergent, then sigma an is said to be conditionally convergent. So we have to see what this series is, whether it is absolutely convergent or conditionally convergent. You know what we mean by divergent. If a series is not convergent, it's said to be divergent. Clearly, the given series is an alternating series because you see negative 1 to the power n starts at 2. If you plug in n equal to 2, you get negative 1 square. That will make it positive. Then when you plug in n equal to 3, then it will become negative 1 to the cube. That will become negative 1. So the series terms are alternatively positive and negative, and it starts off with a positive sign. So we are going to use what is the relevant to this problem, which is an alternating series test. So if the alternating series is given like this, negative 1 to the n minus 1 times bn, where bn is a positive part of every term of this alternating series, then the alternating series converges if the two conditions are satisfied. The first condition is that bn plus 1 is less than or equal to bn for every n. This tells us that the sequence bn is one of a decreasing sequence, and then limit is n approaching infinity bn equal to 0. If these two conditions are satisfied, then the alternating series converges. Whenever we do alternating series test, condition 2 is stronger condition, so we are going to prove that one first. So let's try to prove condition 2. So we will consider limit as n approaching infinity of bn, which is the positive part of the alternating series, which is 1 over ln of 3n, which will be n approaching infinity. We have 1 over infinity, 1 over a large number, which is 0. So condition 2 is automatically satisfied here. What is condition 1? So we are going to show that bn plus 1 is less than or equal to bn. So let's consider bn plus 1, which is 1 over ln of 3 times n plus 1. So we can consider the 3 times n plus 1 is actually more than 3n. So ln of 3 times n plus 1 is definitely more than ln of 3n. So if you take the reciprocal, 1 over ln of 3 times n plus 1 is less than 1 over ln of 3n. So when you the inequality gets reversed when you take the reciprocal. The left hand side is nothing but the n plus first term. Then the right hand side is nothing but the nth term. So bn plus 1 is less than or equal to bn for all n. This proves that the sequence bn is a decreasing sequence. Is decreasing. So this shows condition 1 of the condition 1 of alternating series test is satisfied. So we can conclude by alternating series test. So by alternating series test, the series negative 1 to the power n over ln of 3n, here the series starts only from 2, is convergent. So we have to mention the test and also establish the conditions that are required in the test. And then we can conclude that by alternating series test, the series is convergent. But the question is asking whether the series is absolutely convergent or conditionally convergent. So we have to see whether it is conditionally convergent now. For that we have to show it is convergent but not absolutely convergent. If so, then it will become conditionally convergent. Now that's what we stated over here. If sigma an is convergent but not absolutely convergent, then it is conditionally convergent. So we are going to see whether this condition is satisfied for our series. So we are going to see whether sigma absolute an is convergent or not. Meaning, if this is convergent, if sigma absolute an is convergent, then it will be absolutely convergent. So what we are going to prove here is it is convergent but not absolutely convergent. So let's consider sigma absolute an. So it will be just the bn part, which is sigma without the sign. So you have to get rid of that -1 to the n. That is 1 over ln of 3n. N varies from 2 through infinity. And we have to see whether it is convergent or not. If it is convergent, then the series, the given sigma an would be absolutely convergent. So we can use comparison test here or any other test, comparison test or limit comparison test over here. Now we see ln of 3n is definitely less than 3n. So logarithm of any number is less than the number itself, which we all know. So if you take the reciprocal on both sides, 1 over ln of 3n would be more than 1 over 3n. So when we have two series, and if you have an less than, an more than or equal to bn, if an is more than or equal to bn, and if sigma bn and if sigma bn is divergent, then sigma an also diverges, right? This is what we saw as comparison, one of the statements of the comparison test. If an less than or equal to bn and if sigma bn is convergent, then sigma an would also be convergent. In this case, we are going to establish this result. So if you consider sigma bn, so sigma bn as sigma 1 over 3n, where n varies from 2 through infinity, because the given series starts only from 2 through infinity. So the right hand side series sigma bn looks like a harmonic series, or n to the power p, where p equal to 1. So it's a kind of a harmonic series. A harmonic series, which we all know, is divergent. Therefore, sigma bn being harmonic series divergent. Sigma 1 over 3n, n varying from 2 through infinity, is a p series or harmonic series, and hence it diverges. So if sigma bn is divergent, and we have a relation, this one 1 over ln of 3n is actually the nth term of the given series. So the given series sigma absolute an, which is equal to sigma n varying from 2 through infinity 1 over ln of 3n, which is more than a divergent series, also diverges. So this statement actually shows that sigma absolute an is not convergent. That means sigma an is not absolutely convergent. So what have we proved so far? In this statement, we said that by alternating series, this series is convergent. But here we say the same series sigma an is not absolutely convergent. So 1 and 2 tells that the series is convergent but not absolutely convergent, which is the definition of conditional convergence. Therefore we have by 1 and 2, by the statement that we have proved here, by 1 and 2, the series, the given series sigma, n varying from 2 through infinity, negative 1 to the power n over ln of 3n is conditionally convergent. So whenever we prove conditional convergence, we have to establish two statements, two conditions. One is that you have to prove somehow the series is convergent. You have to also prove the series is not absolutely convergent. So both of them together would mean the series is conditionally convergent. Hope this video helps.